Today, we're breaking down a really fascinating algorithm called sequential attention. What's so interesting about it is that it doesn't just give us a new tool for feature selection in neural networks, it actually goes a step further and challenges a core assumption about how we use attention. And it backs it all up with a pretty compelling theoretical link to some classic methods in sparse approximation. So here's how we're going to walk through this. First, we'll set the stage with the core challenge the paper identifies, what they call the residual value problem. Then, of course, we'll introduce their solution, the sequential attention algorithm. After that, we'll unpack the theoretical heart of the paper, which connects this new method to orthogonal matching pursuit. And finally, we'll look at the empirical results and talk about what this all means for how we think about attention mechanisms in general. All right, so what's the central problem this paper is trying to solve? Well, it's a subtle but really critical flaw you see in a lot of attention-based feature selection methods. See, they usually try to pick the entire subset of features all in one go, and that process, by its very nature, completely ignores what the authors here call the residual value of each feature. So, what exactly is residual value? You can think of it as the extra value, the marginal contribution a feature brings to the table. But, and this is the key part, given the features you've already picked. A feature might look totally useless by itself, but when you pair it with another one, it could suddenly unlock a ton of predictive power. It's exactly these kinds of synergistic relationships that those naive single-shot selection methods just can't see. And this isn't just a theoretical problem. It has very real consequences. When you ignore residual value, your models tend to pick redundant features. Think about selecting two pixels right next to each other on an image that carry almost the same information. At the same time, they miss out on those features that only become valuable in combination with others. So the end result? You're left with a feature subset that's just not as powerful as it could have been. To fix this, the paper introduces the sequential attention algorithm. And the core idea is really to shift our thinking. We need to move away from that single-shot selection and instead use an adaptive, multi-round approach that's built specifically to tackle the residual value problem head-on. This diagram here really shows off the elegance of the solution. I mean, trying to train a whole new model for every single potential feature, that would be a computational nightmare. So the authors came up with this really clever workaround. Notice how at each step, the features that are already in the selected set S just pass right through. But the unselected features, they get scaled by a learned attention weight. It's done with a Hadamard product, an element-wise multiplication, with a softmax output. This one single mechanism lets the model efficiently approximate the marginal gain of all the other unselected features in just one pass. It's really smart. So this all breaks down into a really clear iterative process. You start with nothing, an empty feature set. Then, for a specified number of rounds, you train the model and let it learn attention weights for all the features you haven't picked yet. Then, you just find the feature with the highest weight, add it to your set, and you repeat the process. This is such a powerful idea because it's effectively doing what a greedy forward selection strategy does, but in a much more efficient, differentiable, end-to-end kind of way. And this brings us to what I think is one of the paper's most significant contributions. It's not just about empirical performance. The authors actually build this rigorous theoretical foundation for their method by connecting it directly to a cornerstone algorithm in sparse approximation theory. Okay, so to make the theoretical analysis manageable, the authors first simplify their algorithm a little bit. In this variant, they get rid of the softmax layer and replace it with a direct Hadamard product, and then they add standard L2 weight decay. What this does is it creates a linear, regularized version of the algorithm that's much easier to analyze mathematically. Now, the first step in their proof is to show that this modified, simpler algorithm is actually equivalent to something called sequential lasso. And if you're not familiar, that's a greedy, iterative version of the classic lasso method, which selects features one by one using an L1 penalty. This is the first really important bridge to a well-understood theoretical landscape. And here it is, the main theoretical result. By analyzing the geometry of the problem, the authors prove that for linear regression, their regularized algorithm is equivalent to orthogonal matching pursuit, or OMP. This is huge. It's a really significant finding because it means that sequential attention, at least in its linear form, inherits the strong performance guarantees of OMP, which is a foundational algorithm in sparse recovery. Okay, so with that strong theoretical foundation locked in, let's turn to the empirical results. Because theory is great, but we need to see how it works in practice. And the authors show that the full, nonlinear algorithm delivers state-of-the-art performance on a whole range of real-world tasks.
across a whole suite of standard benchmarks. We're talking everything from biology to image and speech datasets. Sequential attention consistently performs at or even above the level of other leading methods. That includes techniques like group lasso and other attention-based approaches like concrete autoencoders, so it's clearly robust across a bunch of different domains.
The algorithm also scales incredibly well. They tested it on the massive Criteo click-through rate dataset, which has over 3 billion examples. And again, sequential attention outperforms the other methods. This is especially true as you start selecting more and more features. If you look at the plot here, you can see it has a superior AUC and a lower log loss, which really highlights its ability to keep finding valuable features long after an initial set has been picked. This slide gives such a great visual intuition for why this method works so well with neural networks. On the left, you see the pixels that sequential attention picked on the MNIST dataset. They're really diverse, spread all over the digit. Now look at the right. Those are the pixels selected by OMP. See how they're much more clustered and redundant? This is the perfect demonstration that even though the algorithms are equivalent in the linear case, the formulation of sequential attention is just better suited for the nonlinear world of deep learning.
So, after all that, what are the big picture takeaways? Well, this work doesn't just hand us a new algorithm. It actually pushes us to refine our whole understanding of why attention mechanisms are so darn effective in the first place. The analysis really gives us two crucial insights. First, that link to OMP gives us a theoretically grounded definition of what feature importance even means in this context. The attention weights are basically learning to approximate the marginal gain of each feature. And second, and this is really interesting, the paper suggests that the successive attention might not be coming from the softmax function itself, but from the underlying how-to-mard product. This type of overparameterization might be creating a smoother, friendlier loss landscape for the optimizer to work with.
And that brings us right to the final, forward-looking question that the authors themselves pose. If the real magic is coming from overparameterization, then what are the specific trade-offs of using softmax versus other patterns? If we can answer that, both theoretically and empirically, we might be able to unlock even more powerful and efficient model architectures down the road. It's a really compelling direction for future research.